24 hours a day. She is extremely quiet.
Good day to all viewers. Welcome. We are here to pay a tribute to Professor Govind Swarup, father of radio astronomy in India. We have with us radio astronomers, colleagues of Professor Swarup, who will be joining us in time in this tribute session that we have planned from here in the planetarium and as in collaboration with the Astronomical Society of India. Um, in this session, we are planning to have Professor Swarup's interviews reach you, which we had here at the planetarium, and we are having colleagues with us. Poonam Chandra is with us from the NCRA. Divya Oberoi from the National Center for Radio Astrophysics, Professor Dhruva Saikia, and they will all be with you, all of you students, to help you put in perspective the contributions of Professor Swarup to the birth and growth of radio astronomy in India. And you are free to add any queries that you have. Please refrain from having just general chit chat, but any queries that you are free to put them in, and this panel will be taking this. We will just share with you first some video recordings, Professor Swarups, that we
Carl
have.
Jansky in the United States Bell Telephone Laboratory discovered in 1932 that radio waves are coming from the direction of our galaxy. And not much got done soon after. During the World War II, great discoveries took place in electronics, radar, modern equipment. So after the war, people started searching for radio waves from the sky. In 1953, I went to Australia, where there was a beginning of radio astronomy. Some discoveries were being made. I was really fascinated by this field. Radio waves were discovered from directions of very, very distant objects in our sky, much more distant than anything known before through visual telescopes, through optical telescopes. Certain galaxies, there are giant black holes. In our own galaxy, the supernova remnant at the end of a history of a star. When a star runs out of fuel, great big explosion takes place, and supernova remnant gives rise to radio waves. So there are many outstanding explosive events in the universe which are sources of radio waves.
So we will be sharing many segments of this interview, and at this stage, yes, please, Professor Divya Oberoi.
Thank you so much. So first of all, students, it's though it's a sort of a sad thing that we recently had Professor Swarup pass away, but he was always very excited to be with students. He was happiest in the company of students. So it's really a pleasure for us to have this opportunity to reach you. And as you would have heard in his video, he talks about just too many things in a single breath, right? So we'll try to sort of break it down, make it a little easier for us to understand what he's trying to say. So for that, maybe I'll start by requesting Professor Poonam Chandra to first talk about why does one need to do radio astronomy in the first place? Yeah. Poonam.
Yeah. Good afternoon, everyone. As Dev said, Professor Govind Swarup was really a father figure of radio astronomy in our nation, and the vigor and enthusiasm with which he lived his life, he inspires us even in his death. And I'm going to explain some of the things he said in his video. And if you recall, he said he made a point that when Carl Jansky discovered that radio waves are coming from the center of a galaxy, it was actually a breakthrough, because if you try to imagine, you take a step back and try to imagine that when we are trying to understand our universe, the only thing we get from the universe, or for a long time what we have gotten, are just photons. And what we are used to seeing is like the wavelengths for which our eyes are sensitive to, which are called optical wavelengths. So when Carl Jansky discovered the radio waves coming from the center of galaxy, it provided us an entirely new way to understand our universe, to give a new perspective to the universe. And just for that, I would actually like to just very quickly share my screen and show you something, just to make you understand that what I am actually trying to say at this point. And if you can if you look at this image, okay, this is not in radio band, but this is to say my point. If I look at the man on the left, I see his outer appearance, I see his clothes, his skin texture, but I don't know what's inside of him. But when a X-ray machine, if I pass through an X-ray machine, then I can see the internal structure, and this is what is going to give a complementary information. And this is what the benefit was when we had the radio astronomy. Let me just show you this picture. On the left, there is a galaxy which is seen in the radio waves, in the optical, and you see it looks like an ordinary galaxy. And when you look in the right hand side, it is a radio image on the same scale for the same galaxy. So one can see a very different view of our universe with these radio waves, and this is what radio astronomy facilitated us with. And also in this, Govind mentioned something very important, that when you have radio astronomy radio wavelengths available to you, you can probe the part of the universe which are unavailable elsewhere in other bands. And one of the things he mentioned were explosions, supernovae remnants, and central supermassive black holes inside the galaxies. And these are the things which radio astronomy is very well suited for. And I don't know, Professor Obira, you tell me, this is the right time to explain the explosions and all, or should I just wait to talk about it at a later stage?
Yeah, I think, yeah, we will also have Professor Swarup, when he's about the beginnings of radio astronomy, and then we will come to these aspects as we go along. Is that all right? Shall we do that? Let me just
Well, I came back
Sure.
from Stanford University, 1963, and Dr. Homi Bhabha, the father of atomic energy in India and who built the Tata Institute of Fundamental Research, he approved formation of a radio astronomy group in Tata Institute. And he had written to me when I was Stanford University that if you meet our expectation, we can have much bigger equipment. So whilst 1963, there was a great big controversy how our universe is formed. There was a theory Hubble had said, further away a galaxy, faster is moving away. That means to begin with, all galaxies, all stars, all of us were in a tiny, tiny point. And then Big Bang took place, and that's what the universe is. But Fred Hoyle from England, Cambridge, he said, well, why the matter has to be created right in the beginning? Maybe it gets created all the time in all places in the world. So it was a great big controversy. She talked to me with Dr. Homi Bhabha's great vision for India, that I should do something truly outstanding. So I got an idea of building a large radio telescope in southern India, taking advantage of India's closeness to Earth's equator. So that's how the beginning of radio astronomy, and I built the OT radio telescope.
so
Wow.
before.
Yeah, so that's really fascinating. So the birth of radio astronomy in India was really related to the burning topic of that time of finding the nature of our universe, Big Bang versus steady state. Poonam, would you like to talk a bit more about that? Yeah.
Of course, of course. So, just to give you a little bit of perspective that what this whole dilemma was. So, in 1940s, 50s, and 60s, people were trying to understand our universe, and there were two kinds of theories which was propagating. And for that, I will again share my screen and just show you with visuals what I mean. So there was two kind of theory. One theory which said that universe has a beginning and a starting point, and that kind of a universe, that kind of a theory was a Big Bang theory, that universe started with a Big Bang explosion and all the matter was created at that very beginning of the universe, and universe is evolving since then. That is the Big Bang theory. The another theory which Fred Hoyle believed in was steady state theory, which said that universe is as it is, has been what it is now, and matter is being created always since the very, like, it has been being created, and this is how the universe is. Now the interesting part here is that there are some very clear predictions of the two theories. If you look at this slide, if matter is being created and universe is expanding as per steady state theory, the top panel of the figure, then universe is getting bigger and bigger. But since matter is being created, the density of the universe does not change. But if you look at the bottom panel, which is what Big Bang model predicted, if everything got created at the very beginning and then universe is expanding, the things will start to get far away from each other. It means, in other words, the density of the matter of the universe will decrease with time. Now there is a very, very beautiful prediction, observational signature of this. If a steady state is correct, then the objects which we see now should be visible in the past, back in the time also, and all the time you should be able to see. But in Big Bang, there should be some things in the past, but not now. So the problem is that optical astronomy cannot go that far back in time, because there is a lot of extinction. Even the dust is there in the universe, which absorbs optical light. But radio could go to these things, and there are some of the very bright radio objects like quasars, radio galaxies. These are one of the best things to look with the radio telescope now and way back in time, and then try to look for these objects and try to distinguish between the two models. And this is what the radio astronomy was set out to do. This is what Govind had in mind, to look for the quasars in the past and now, and see where do we stand at that point, at this point.
Yeah. Professor, as we go forward to learn about the OT radio telescope, Professor Saikia, would you give us some insights about the very beginnings of radio astronomy in India? Your mic is muted.
Okay. Good afternoon to all of you. And the beginnings of modern radio astronomy in India, as Div mentioned and you all mentioned as well, started with the efforts by Govind and a few of his colleagues to set up modern state-of-the-art radio astronomy facilities in India. And as he mentioned, that there was a very strong desire to come back to India, although he was doing very well in the States, outside the country, and set up facilities over here. And one of his very strong points was that he wasn't buying things off the shelf. He was also trying to find ingenious solutions, make things with his own hands, and developed excellent teams, both while building the UT radio telescope and the giant meter wave radio telescope. But the beginnings of Govind's work in radio astronomy started in the National Physical Laboratory itself, where a small team had got together, and he had also tried to he had got the dishes from Australia for one of the Australian telescopes where he had worked briefly. And that was actually the first instrument which he built. The Australians had gifted the dishes to India, but there were issues about transporting it from Australia. And in those early days, India was so short of foreign exchange that they couldn't afford it. And ultimately, the Australians shipped it at their own cost. But these dishes were used by Govind after he came back from the States to set up the Kalyan radio telescope, where my colleagues Vijay Kapahi, who passed away, and J.D. Islur, they were amongst his very early students who worked at the Kalyan radio telescope. And this was largely meant for observing the sun. But of course, these were the very early beginnings. And as Baba also envisioned, and Govind also sort of spoke at length, that they were trying to think of much bigger things to do. And much bigger things to do were to address the burning questions of the day. But when you build a versatile instrument, there are a wide variety of things which gets done. And although the motivation, as Poonam outlined, was to try and answer the big question about the steady state versus the Big Bang cosmology, where the Big Bang had its origin in one singularity. In fact, the word Big Bang came from Fred Hoyle, who actually derisively said, "Oh, Big Bang," about the Big Bang theory of the universe, because he was the proponent of the steady state model. And then on to the GMRT. So a lot of questions. So a lot of those were the sort of early beginnings, starting at NPL, setting up Kalyan telescope, and then on to UT, and later on to GMRT.
After a lot of search, we found a hill in Uttarakhand in South India, which is in the north-south direction. It is a slope of 11 degrees, which is the same inclination as the latitude of the station. That means the parabolic cylinder rotated telescope, which you see in the picture here, has the north end is towards the North Pole, the south end points towards the South Pole, of course, below the Earth. So in that sense, the parabolic cylinder, the long axis of rotation, is parallel to the axis of Earth. So as we rotate the telescope, we can follow the source continuously. In the north-south direction, as we want to see various north-south direction, we use electronic phasing, which change the delay line. There are 1,000 dipoles at the focus of the parabolic cylinder. I mean, instead of a heating rod on a heater, which you see in North India in the winter time, instead of that, there are 1,000 dipoles at the focus of the focal line of the parabolic cylinder. And by changing the length of cables from each to the receiver room, you can point it to the north-south direction, some direction. And then by rotation, you can follow the moon.
Yes. We'll just see as we get to discuss UT radio telescope. This is been taken from Ajay Talwar during the annular solar eclipse of 2019, and what Professor Swarup was mentioning about the tracking. So this visual, and then I'll hand over to Professor Divya Oberoi to lead us through the dynamics of the UT radio telescope.
Sure. Thanks a lot. So let's understand a little bit the working or the UT radio telescope itself. So first, you have to actually realize that these radio sources which astronomers want to look at, they are really very faint. So you need two things. You need to build something huge, what you might call a light bucket, right? If it's raining, you keep a bucket outside, some rainwater will collect in that bucket. And the larger your bucket is, more rainwater will you be able to collect. So think of a telescope which is collecting the light which is coming from these astronomical sources. Larger is the aperture or the area of the telescope on which this light is falling, the more sensitive your telescope would be. So because Govind wanted to do he wanted to look for very faint, very distant sources, he needed to make something very big. But then, and let me share my screen to make it a bit easier for me to explain. Right, we are sitting on the earth and the earth is rotating, right? So if I want to stare at the same place on the sky, I have to do something to compensate for the rotation of the earth. So the picture which you see here actually was taken in Ladakh at one of the Indian observatories, and you see there it's about a 7-hour exposure, and all these circles you see are what a single star trail is looking like. A star has moved in the sky, or it seems to move in the sky because the earth is rotating, and the only point at the very center which does not seem to be rotating at all, as seen in this picture, is the North Pole. And because an astronomer is trying to look for very faint signal, you are going to want to build something very big and then look at the same source for a long time. It's just like taking a night exposure with your cell phone or camera, which needs to be much longer than when you're taking an exposure during the day. So a crucial requirement for a telescope is that it must compensate for the rotation of the Earth. Now, if you imagine, if you're sitting at the equator, the tangent plane parallel to the equator, if you were to just draw a straight line flat on the surface of the Earth, that would actually be parallel to the equator itself. But if you were to move to a higher or lower latitude, what you need to do is that you need to find a mountain which is sort of north-south, such that, and its slope is equal to the latitude of that place, so that if you were to place something on that hill, you would be able to build something that its north end would point exactly towards that North Star, and its south end would point exactly towards the South Pole, or the southern celestial pole, and that would make it very easy for you to compensate for the rotation of the Earth. And that is the telescope which you just saw a picture of. So it is something which is half a kilometer long, 530 meters, and it is 30 meters wide. Right, so that is the size of this telescope. Imagine building something which is of this size and which can be moved precisely. That's really an amazing feat. Now you'll wonder, a telescope is supposed to collect radiation, which is light which is falling on it, but here there does not seem to be anything like this, right? I can see right through this telescope, and that is the beauty of working at these low radio frequencies. The mirror of this telescope is actually composed of these stainless steel wires, which you can probably barely see here, and you can see actually a reflection of the sunlight from those. So there are 1,100 wires which are running across these parabolic frames, right, from which light is being reflected and brought to these 1,000 dipoles, which Govind mentioned as he talked about. So, so you can have essentially a mirror for this telescope, which to our eyes seems transparent, but for the radio waves we are interested in, it's a pretty good mirror. Now, there's one more thing which he talked about, which I just wanted to take a minute to explain, which is that, so this will take care of the fact that you can compensate for the rotation of the Earth. So you can make your telescope go from west to east, and that is all very good. But how do you choose which direction to look at along the north-south axis, right? So for that, take a look at this diagram. So imagine that there is a wave which is coming from the top, and it is coming exactly parallel to the telescope. So as this wave comes down and hits the telescope, it will hit all parts of the telescope at the same time. But if you had something which was coming from a different direction, say a wave, you wanted to look in this particular direction, so this wave which is coming towards the telescope, it will hit one end of the telescope earlier and the other end of the telescope a little bit later. How much later? That depends on how much time does it take light to travel from there to here. Now, light is a wave, and waves have these crests and valleys, as we call them. So if I can delay the signal coming from this part of the telescope by exactly the amount that when I add them all up together, the total time which has taken for the light to be detected at my telescope and to be added up here, it compensates exactly for the additional path length which this light ray has taken to travel to different parts of the telescope. This is what Govind was talking about when he was talking about adjusting the phases of the telescope. This is the technique which is used to point the telescope from anywhere along the north-south axis, or the so-called declination axis. Okay, not sure, maybe my screen is frozen here. Okay, yeah. I think that's what I wanted to say at this point. I'll pass it back to Ratnashri here.
Yes, and actually, will be Professor Saikya, if you wanted to add uh, from the UT days any inputs, and then we will be moving on to the next phase, the GMRT. So I just wanted to check with you if you would add
Okay.
input, any recollections from the UT
Okay.
early days.
Uh, okay, just very briefly, actually. I joined Govind in 1977, and those were not the very early days of the UT radio telescope, because the telescope was constructed and had made seminal discoveries by then. And just to refer to the question of answering questions of big science, and also Divya's point that he was trying to look at very faint sources, and Poonam's talk about the Big Bang theory versus steady state. I'll just speak very briefly about the excitement of those days and trying to link these together. Because what happens is that depending upon a particular cosmology, that that sources will appear different if they are at different distances from us. And weakness was important because if you take a certain source of a certain brightness or intensity, you can think of it as a candle, you take it further and further away, it becomes dimmer and dimmer. So the more distant an object is, the fainter it is going to be. And what happens is that when you go further away, the difference between the different cosmologies show up more clearly. Now, to do that, you had to measure the sizes of these objects very carefully, and this was almost not possible at that time. It was a challenge, and to measure sizes, you also need what is called resolution, to ability to see
Yes.
detail. And for example, our eye has a resolution of about an arc minute or so, and that is because of the optical region of the wavelength that you're looking at and the size of our eye. If our eyes were much bigger, our resolution would be much better. So the size of the telescope normally determines also the angular resolution or the ability to see detail. But to answer Govind's question, or the question he asked himself to build a big instrument about measuring sizes of radio sources, was difficult and challenging. So he came up with this technique, which was used earlier, but he developed it and exploited it in UT, was to look at the sizes of sources when they get occulted by the moon. So
Yes,
this
I was going to play a video of
okay.
Professor talking about that. Shall I do that?
Okay, I
Yes.
think you can do that.
Yes.
So why this elaborate thing?
Yeah.
Because we wanted to measure angular sizes of radio sources to distinguish between the Big Bang and steady state theory of the formation of the universe, and a unique challenge at that time. And most radio galaxies are double radio sources. As moon moves in the sky, it first eclipses or occultation, as we say. It first eclipses one part of double radio source, the second part, and later on, after half an hour or 20 minutes, the moon has moved away, and the sources come, the two double sources then again come out. So by that we are able to measure angular size of radio sources. And then during the telescope was conceived 63, completed 1970. It was the first radio telescope built in India. It was very large, it is still existing in a beautiful hill of Uttarakhand. It had 4 times the area of the famous Jodrell Bank radio telescope in England. and is still doing extraordinary experiments. It has discovered many pulsating radio sources and also everyday measures scintillation of quasars and other point sources to measure the velocity of the solar wind taking place, particularly after big flares. The solar wind comes sometimes. If the great big storms take place, we call coronal streamers. If they hit the Earth, they affect the communication, they affect the satellites. So Ultra telescope is one of the unique instruments in the world working today for advanced warning of such solar storms.
So, Divya, you wanted to add about the lunar occultation study
Sure, I
and
can.
tell us
Yeah, I
about
can
that?
make one point about that. So, how is it that one is able to use this thing called lunar occultation to understand the structure of a source, right? So, that's something which many of you will learn as you proceed in your classes and learn more physics. So, this is because of the so-called wave nature of light. If you have, let's say, a very sharp edge of the moon, and there is a source which is at the background, which is slowly going to hide behind the moon, just as it is hiding, as it is coming very close to the edge of the moon, naively one would expect that, well, till the time it is just behind the moon, I'll get all the light from the source, and just as it goes behind the moon, I'll get no light at all from the source. But in reality, what happens is that you actually see some variation in the amount of light which you are receiving from the source. The exact details of that variation are telling you about the structure of the source. Like Govind was saying, that most of these sources are actually double sources. They have sort of two components close to each other, sometimes another third thing right in the very center as well, which you can see. And so by examining how this light is varying, just as the source is going behind the moon or appearing from the other side coming out of the eclipse, you are able to actually determine their angular size. It's a truly exciting way of being able to get very high angular resolution using a single large sensitive telescope. Yeah.
Well, Uti radio
Yeah. And
telescope became functional in 1970, and it occurred to me, there were, of course, in science there are always new questions, new theories, new challenges, and whatever we know is so little. There's always there are theories who have ideas what their theories are great people. But on the other hand, unless we do experiment, unless we do observations, how do we know what's the truth? So it occurred to me to build a much larger telescope, 2 kilometers long, 50-meter wide. So I proposed building a giant equatorial radio telescope at the Earth's equator in Kenya. And it was approved by UNESCO, by Government of India, agreed to give half the cost. But then Kenyatta, the founder of Kenya, he died during the negotiations. They went to Indonesia, but then the earthquake is there, a lot more. So finally, we had designed.
Oh,
Now the bigger challenge took place. By 1970s, microwave background had been, 1965, microwave background had been found, which is a subject by itself. And so the question to Big Bang, it was very clear from our experiments at UT and also by discovery of microwave background that the universe was formed by Big Bang and not by steady state. In Big Bang, matter is supposed to have been originated right from the very beginning. And is there only our universe? That's a different subject. There may be other universes like ours. And but then the question comes in, what was before stars and galaxies? So according to the Big Bang, when the universe was about at temperature of about billion degrees or 10 billion degrees, electrons and protons got formed because the temperature has similar energy as required to form electrons and protons. And later on, the universe was expanding. So electrons and protons and what you may call gas of elementary particles, it cooled. And later on, one electron, one proton forms hydrogen gas. So to begin with, there was only 75% hydrogen gas and 25% helium, of course, in extremely vapor stage. But then it cooled. When it cooled, it started collapsing. But if you keep on cooling, clumps take place. So because universe is, the gases are rotating, they collide with each other, and they form clumps by gravitation. Gravitation is a very powerful force. So by gravitation, electrons, protons combine together. If they're cooled enough, they form the gas. So by 1980s, it became very clear that that is the way galaxies and stars form. Now, if it is true, we have to find these hydrogen clouds before stars and galaxies, because then we will be able to show how stars and galaxies form. Now, hydrogen, cold hydrogen, is so cold, it does not give rise to light, but it has a unique signature. It gives rise to radiation at 21 centimeter wavelength, or what we call 1420 megahertz cycle, about 100 times, about 10 times shorter wavelength than that of FM station. And so electrons and protons, they both spin around each other. They say they're like little magnets, and if they flip, gives rise to this wavelength. So no other radio telescope existed in the world to search for such massive hydrogen clouds. And so once we were very successful at UT, and we have formed a powerful group, building everything locally, nothing imported, except instruments, basic things like transistors. We had now a mastery on the subject. So I conceived first of the giant equatorial telescope, and that I could not build, could not find a suitable site elsewhere in India. So I conceived of giant meter wave radio telescope to be built somewhere in India, like a Y array. And so the search for massive clouds continues at UT, and some furthest away hydrogen clouds have been found at UT, with the GMRT. Also, in the beginning, there were not only massive galaxies formed, but they evolved, they changed all the time, like men grow, children grow. So they are different. It's very interesting to see what were the earliest galaxies. So in the universe, there are what is called dwarf galaxies. These are small galaxies. And so some massive work has been done. Very important work has been done. And so GMRT has has discovered many new results. And to tell in short, it's being used by 32 countries in the world, including scientists from India, people from Cambridge, Oxford, Harvard, Stanford, Japan, China, Russia, Italy, Germany, Brazil, Argentina, Chile. They all come to use Canada because no other instrument exists like that at long wavelength, giant meter wavelength telescope. Why we built at meter waves? Because shorter the wavelength for a given instrument, you can have a better resolution. For example, only a 10 centimeter optical telescope can give you a resolution of 1 arcsecond, but radio waves of 1 meter wavelength require a 200 kilometer size telescope because the radio waves are much larger. So 1984 was the beginning of GMRT. I realized that no other instrument which can do, there are many outstanding experiments which are best, there are many outstanding questions about the universe which can best be answered at long wavelengths. And what is the advantage of, there's no snow, so we can put very thin wire mesh, so wind passes through, but radio waves get reflected. And such, so there's an advantage of building a large radio telescope in India. Besides, the radio noise was much less. So 1984, I proposed, along with some younger people, colleagues in Tata Institute. 1987, Rajiv Gandhi approved it. And we started designing it. 1990, first fabrication started. By 96, all 30 antennas of 45 meter had been built.
Yeah. Divya, as you walk the viewers through the dynamics of GMRT, I will try and see whether there are student questions so that we can include them also as we go along.
Sure.
And
Yeah.
if you need visuals of map visuals, I will try and provide that for you. Let me hand over to
Sure.
you.
Thanks. Yeah. Thanks. Yeah. Okay. So yeah, there's just far too many things which Govind covered in the past few minutes. So let's just pick up a few of them and maybe learn a little bit more about them. Right. So one of the things which he said just soon after the start of this set of videos was about the role of theorists versus experimenters. Right. So I just wanted to highlight to you that both of these aspects play a very important role in the progress of science, right? Any theory which is proposed has to be verified by an experiment, and any observation which an astronomer makes or any lab makes that observation or conducts an experiment and gets some results, those results have to conform to some theory. They will either prove or disprove some theory or put forth some facts which are not explained by a theory, and therefore is a challenge for the theorists to come up with an explanation for them. And so this process goes in hand, and therefore with progress of technology comes progress in science, because progress in technology towards making a telescope means that now you can measure something which was impossible till some time back, right? And here the challenge which Govind was trying to meet now was to detect the first galaxies, the first stars which would have formed, right? So we all know that stars give out light. This is a time when stars have not yet formed, because the universe is still a bit too diffuse. So he wanted to look for these clouds which would become the first galaxies. And for that, maybe I'll just share my screen for a bit and tell you something about the signal which one can use for that. Right, we know that hot things give out light, but cold things don't give out light, right? And that's a problem. So if we want to look for cold hydrogen, because like Govind said, 75% of universe was really hydrogen, how will we ever detect it if it does not give out any light? Because as an astronomer, we're just sitting on Earth and we are waiting for light to come to us. So we can only see things which give out light. And mercifully, there is this radiation which we can see even from cold hydrogen atoms. So what happens, as all of you know, hydrogen has a neutron and a proton, and both of these things, both the neutron and the proton, actually spin. They have an attribute called spin. If the spin of these two things are aligned to each other, it is in a slightly higher energy state as compared to the state when the spin of the neutron and the proton and the electron are opposite. Okay. And when it goes from the excited state or the high energy state to the low energy state, it gives out a tiny amount of light. This light has a wavelength of 21 centimeters or a frequency of about 1420 megahertz. But one problem is that this is a very weak transition. By that, what I mean is that if you were to look at just one atom, you have to wait on an average about 10 million years before it would actually do this transition and give you some radiation. Or another way of saying it is that if I have 10 to the power 15 such hydrogen atoms, only one of them will show me this transition in every second, right? So even though there is a lot of hydrogen, this signal is still very weak. Therefore, you need to build a very, very big telescope to be able to answer this question, right? And that is why Govind was thinking of the giant meter wave radio telescope. Something that big never existed in the universe on our planet. And even now, there is no other telescope which is as sensitive as that. There's one more thing which you need to know to understand this. So the GMRT works from about 1420 megahertz to lower frequencies of till about 150 megahertz. Many of you have probably heard of something called the Doppler effect, right? The visual on your screen should remind you of something, right? You have an ambulance coming towards you. It seems to you that the pitch of the siren is actually a little higher as compared to what you would hear if the ambulance was stationary. Or if it is going away from you, you think that it is a little bit lower. The pitch is a little bit lower as compared to what it would be if it was standing still, right? This effect, as perhaps many of you know, is called the Doppler effect. And so if something is moving towards you, its frequency seems to increase. And we call it blue shift because this suggests a shift towards the blue part of the visible spectrum, which is shown here in the lower panel towards the left. And if something is moving away from you, the frequency of that shifts away, shifts towards the red part of the spectrum, and that is what we call the red shift. And as you know, Hubble had already found out that the further something is, the faster it is moving away from you. Therefore, the further back you want to look in space, that would also become further back in time. It would mean that the signal you are looking for is going to appear at lower and lower frequencies. That is why GMRT was designed to go from 1420 megahertz, which is where this line would be if something was at rest with respect to us, to lower frequencies where this line would shift if something was moving further and further away from us, right? Maybe at this point, I'll take a quick break and ask Ratnashri if there are any questions which she would like us to take.
Yeah, I was scanning through the questions, and there was one student who was asking how he can become a radio astronomer. And I just wanted to mention to all the viewers, all the students, you now go ahead and place your questions as text under this. The previous one, there are a lot of hello messages, so I'm finding it difficult to find the questions. So students, please go ahead and place your questions now. There was a student who wanted to know how he would become a radio astronomer. And maybe if the panel would give some advice, and then we will also have one more video segment from Professor Swarup talking about further usage of GMRT and so on. Please.
So, Professor Saikia, may I request you to address that question? How do I become an astronomer? Yeah.
Okay. No, it's actually absolutely lovely to hear young students being excited to become astronomers, and particularly radio astronomers. Okay, I think there are various things. One thing is, of course, to do something well in life, you need to be driven by excitement and curiosity. And these are things which you got to inculcate from a very young age. It doesn't matter whether you're looking at the cosmos or the universe or the butterfly in your garden. I think there are always questions you can ask yourself. And this curiosity driven, which Chandrasekhar Venkat Raman also emphasized to an extent when he talked to young people, is something which is essential. Then in terms of contributing later in research, in addition to being always querying, asking questions, you have to develop a base of knowledge. And in this base of knowledge, it depends on what are the areas that you would like to be motivated by. So essential, I think if you want to look at the physical aspects of it, a good training in physics and maths is important. And for example, if you want to look at engineering aspects, then the relevant branches of engineering. But today there is a lot that is happening which has to do with computing. So I think developing a broad base of knowledge and expertise, obviously things have become so specialized that one cannot do everything. But I think the primary things would be determined on what specific aspects you want to sort of focus on, and this will develop as time goes on. But I think it is important not to lose your enthusiasm. Be always curious, be ready to ask questions, and never shy away from asking a question. Doesn't matter how dumb it may seem to you. Always something which we learn, even when we are trying to address questions from young students.
So there is Hansrud Gupta. How are many radio telescopes in different parts of the world connected? That's a question which has come in. Was I
Okay.
audible when I said that? Yeah.
Yeah, you were audible. So is the question simply how many telescopes are there in different parts of the world? There was also connected at the end of the question, which makes it a sort of very different thing. But to answer the first part of the question, so there are maybe less than 10 big radio telescopes in the world. Okay, the exact number I have not tried to count, but I'm pretty sure they'll be less than 10. These are the so-called interferometers, which basically they are like GMRT. They have many telescopes which are spread over a large geographic region, and they make a map of the sky. Okay, these are sort of very expensive instruments, and one very nice thing about these radio telescopes is that you don't have to be at the institution which made them to be able to use them. You can be anywhere in the world. Most of these telescopes follow what is called an open skies policy. You propose what you want to do, a panel of experts will evaluate how good your proposal is. If it is among the best ones which have been received, you will get the time to observe it. Even Govind, if he wanted to observe with the GMRT, had to go through the same procedure, even though he built the telescope. Okay, so that is how, because all of these radio telescopes are trying to get the best science out of these instruments, and there is no charge for using the telescope. You talk about the science which you want to do. If it is good, you will be able to use it.
There is a viewer who is asking, can you tell us what are radio telescopes? As there are many young school students,
Sure,
maybe if you
yeah.
just tell them what exactly are, what is being detected, it will be useful.
Maybe I can share my
Yeah.
screen to show exactly what radio telescopes are, because this is something,
Please, yeah.
I
Yeah.
think it's quite exciting to know. So if you look at this slide, on your right, there is moon in optical, and on your left, there is moon in radio. And you can hardly make out anything what this moon is. The problem, this is how it is, because radio wavelengths are very long. And you may have read in your physics classes that resolution is lambda over d, where lambda is the wavelength, which means that to make a radio telescope which can give you a good image of celestial objects, you need to have built very, very, very big telescopes, like 25 kilometer, 30 kilometer telescopes. It is not possible to do that. It is practically not possible to make a dish which is 25 kilometers in diameter. So what radio telescope, which is based on a principle of radio interferometry, is to build multiple telescopes which are rather small in size and then make them work together. Okay, and this is by something called principle of interference. But this is how actually I want to show you. This is how a GMRT is. On the top, you will see some 5-6 dishes. But GMRT doesn't just have 5-6 dishes. It has 30 such dishes. These all dishes are spread in 25 square kilometer area. Now each of these small dish you can see is 45 meters in diameter. But these 30-45 meter diameter dishes, when they are working together in 25 square kilometer area, they work as practically as one single dish of 25 kilometer diameter. So this is what a typical radio telescope will look like, which will have multiple dishes. And on the right, what you see something moving, a Y kind of array, because this is showing you that this is how GMRT is. These 30 antennas are spread in something called a Y-looking array. And now, if these antennas are looking at a source in the sky and our Earth is moving, so suppose you are observing a source for 8 hours, Earth has already done one third of its rotation. So you will see, practically you will actually cover a much larger uh, part of that big antenna, and this is called aperture synthesis. And on the left, I am actually showing you that how GMRT antennas are moving. I don't know why it is not showing, but it should show now. Yes. So you may see these GMRT antennas are moving. So these are movable, steerable dishes which will track the source in the sky. And as the source will be seeming to move in the sky because of Earth's rotation, the antenna will also move so that it points toward that location. So this is how a typical radio telescope will look like.
We probably should take up this question too from Hansrud Gupta. Most of the radio waves are filtered by the atmosphere. Well, actually, it isn't fully true. So maybe our panel will take this.
Yeah. So I think Poonam has a slide which talks about that here.
I do. Yes, I do have a slide, and I'm going to share that slide right now. So let me just do that. Okay.
Yes. And then I also see that there are several general astronomy questions. This is just to tell the viewers that we will be taking these up perhaps in some of the following sessions. We will be concluding the session
Yeah.
after this question.
So as you can see, this is our Earth on the bottom of this figure, and this orangish yellow part is the one which is opaqueness of the in a different wavelength. These are different wavelengths. The x-axis or the horizontal axis represent the wavelength higher to lower frequencies or lower to higher wavelengths. And unlike your question, what you can see that it is only the optical and the radio, where or you see this big dish on the right side, where these can actually come to Earth without getting absorbed. So contrary to what you said, radio, it is X-rays and gamma rays which gets absorbed by Earth's atmosphere. But radio wavelengths can totally pass through Earth and can be observed on Earth.
Yes. So some of the other questions, viewers, we are going to take them up. There are X-ray telescope. There are general questions. We will collect all of them and we will take them up in subsequent sessions. I think we would ask for concluding uh, tributary comments from all the panel members.
So, Professor Sykes, may I request you to go first? Yeah.
Okay. No, no, I think it's an occasion to pay tribute to Govind, who's been very correctly called the father of radio astronomy in India. He not only built world-class telescopes to address some of the key astronomical or science questions of the day, but he was a person who was always ready to interact. In fact, particularly to the young students, he thrived in that. And if you got caught in the corridors, I mean, you could easily spend half an hour to an hour discussing one of his latest ideas. In fact, he came up with an idea almost every day, probably. And like all people in science, not everything works, but he was always a thinking and person, always thinking of new things and fresh things to do. And although in this tribute today we have largely focused on telescopes and science, his contributions have gone well beyond that, because in fact, the joint astronomy program for astronomy students who want to learn astronomy and astrophysics was initiated by him. One of the first summer schools on astronomy and astrophysics was due to his initiation. He laid the groundwork for what are today the renowned ICERs, the Indian Institutes of Science, Education and Research. And I still remember the very early days when he and Professor Bhide from Pune University were actually laying the groundwork for what later became the ICERs. So astronomy, science education, building telescopes, mentoring individuals, and a remarkable trait to actually get young people together and build these instruments. The average age when UT was being built was probably about, less than 30, 26, 27 or so. And these were the kinds of people whom he interacted with, whom he mentored, whom he motivated, and built his instruments. So it's not difficult. It's not easy to find a person like him today. The world has changed, technology has changed, and what is amazing is that Govind has, over the years, he has adapted to these changes so very well. We were in the days when letters were sent by snail mail or letters we'd write in longhand. Then came were faxes, telexes, and now WhatsApp. And Govind was, highly active on WhatsApp. In fact, the last message I got from him was just a couple of months ago. And he's an amazing adapter. He's an amazing learner. Far after he had actually officially retired, he wanted to really master one of the astronomical image processing systems called APES. And those are his traits. I mean, it's a journey of learning always. It's a journey of learning, teaching, educating, exploring new frontiers. That is a man we'll all miss at a professional level and also at a very personal level. He was a caring individual. He was supportive of what we did. And with these, I sort of close my remarks, at least as time is running out. Thank you very much.
Thanks.
So, if you wish to take up, there were also a couple of questions, and also if you wish to take that up, Divya.
So
And
I'll quickly take up the last one you flashed, which was about how do radio waves transmit data several kilometers away. So I believe that is about how does it get, we have to gather data from all these telescopes, which are distributed over 25, 30 or even more kilometers. That data is put onto optical fibers and carried back to a central location where it is processed. Earlier in the days, it was being carried over something called waveguides, but these days practically every instrument in the world, with GMRT being the pioneer there, these data are carried over optical fibers. With that, maybe I'll ask Poonam to say what she would like to say about Govind here.
I would be extremely short, but I will give you a glimpse of what Govind was. So, right now, there was just some time back, there was a question that how do I become a radio astronomer? If Govind was in this panel, he would have directly contacted that student, taken his phone number or email, and himself written to the student that come and meet me, and I will tell you how to become a radio astronomer. This is what Govind was, and this is all I want to say right now. This is how inspired all of us.
yes, yes. I mean, we would see it at the planetarium from the heights, very heights of cutting edge technology, innovative, that brilliance. But he would always, for any child who is asking a question, he was always there. He
Yes,
insisted that we should give our
yes,
full
yes, yeah.
to him.
Right.
Yes. And I just want to tell the viewers that we are having a follow-up session. If you are interested, please do come for that too. The link for that session is going to be put just under this as a comment once the session concludes. So you can join in with us there. And I wish to thank all of you who are here to lead the viewers through, Professor Saikya, Divya, and Poonam. Thank you very much for being with us, and thank you all of you students for being in this session. And please come in the follow-up session too. So some of your questions may be taken up there too. So we will be ending